next presenter is Mr. Muhammad Fariz Sutedy, Mr. from Bina Nusantara International University. Okay, Mr. Muhammad Fariz, the time is yours.
Okay. So everyone could see my slide?
Yeah.
So, good afternoon everyone. My name is Muhammad Fariz Sutedy from Bina Nusantara International University located in GWC Jakarta Selatan. First of all, thanks and congrats for the 5th event of ISRITI and huge gratitude to University Teknologi Digital Indonesia for organizing this big international event. So this is the title of my paper, which is Latent text-to-image latent diffusion model with fine-tuning for automobile image generation. Today, I'm also in the name of another writer, Ms. Komaria, who collaborated with me to build this paper and research. So in the next slide, this is all the topic that I'm gonna share with you guys. So basically, this is the 4th chapter that we have written in the paper, starting with introduction, methodology for all important models that have been used to smooth this research. Then there are result and discussion, and lastly but not least is conclusion. So what is text to image? Basically, text to image is a machine learning model that takes a natural language description as input and output an image that matches that description. As a result of a breakthrough in the deep neural network, such concept began to emerge in the mid-2010. When generative adversarial network or GAN model were made, so basically the goal of the text-to-image generation model is to generate photorealistic images that are semantically compatible with the text description. And with the example model, like I said previously, there is a GAN and also Phi model. GAN and Phi are a couple of models that are quote-unquote born early, rather than the newest one like diffusion model. From the diffusion model, there is a latent diffusion model that comes in 2021. For the background why we use LDM, the reason is because it's the most recent and the better than past models. Like been explained before, the LDM model come early in 2021. Also, why LDM is currently better than GAN is because diffusion model produce even better realistic image than GAN. Diffusion models are more faithful to the data in the sense while GANs get a random noise or class conditioning variable as input, and then produce the realistic sample. Diffusion models tend to be much slower, iterative, and much more guided process. So, why combine LDM and the Dreambooth? So, before that, many researchers did the LDM model without doing the pre-training first. One of the big reasons this step is so important is because the LDM model is disturbed by a possibility of overfitting and language drift. To tackle the problem, we pre-trained first the model with that is called Dreambooth fine-tuning. Later on, the explanation of Dreambooth will be explained more in another slide. So, why this project? With combining LDM and Dreambooth, optimism of giving a new ways to generate text to image could be made because of the researchers that never combined these two models before. The expected output of this model can use to generate image of automobile in the predetermined location with several characteristics, for example, like the position of the car, colors, models, makers, or type. So, this is our flowchart in this research. The project starts with data collection and processing, pre-processing that would be done in collab environment. First, import the LDM model and pre-train the model with Dreambooth. Before training the model, then there was several hyperparameters that need to be filled. For instance, the epoch, learning rate, and initial learning rate. After the training, test the result by calculating the MSE and the RMSE score in the TensorBoard. Lastly, a simple UI has been made to generate text to image. In this methodology session, we are going to dig deeper in some steps like data collection, LDM, Dreambooth, and Exformers, and learning loss, which is MSE and RMSE. So, in this study, a dataset created by a data scientist named Nicholas Gervais in January 2020, then before being processed into the training, pre-process the data done by selecting the broken image, like image that broken too much, or maybe zoom in, or maybe only saw the few part of the automobile and the interior automobile. This is being done to make a better model for our research. Finally, we could use around 1,200 images with the 49 different brands of automobiles. Next, a size change before importing the image into our model. Before beginning the training, equalize the image size by using 512 x 512 pixels for each size. Also cropping the center of out of every image to make the training process much simpler. Next, we go to the model that is being used, which is Latent Diffusion Model, or LDM. Functionally, LDM enable the training of diffusion model with limited computational research while maintaining their quality. Instead of operating in the high-dimensional pixel spaces, LDM work on the latent space of transformer model, which is highly compressed. LDM are composed of two main phases: the perspectual compression phase, which use autoencoder to remove the high frequency detail, and the semantic compression phase, to which they refer knowledge from the composition of the data. Next one, yeah, we we jump into the Dreambooth fine tuning. Many past researchers may pre-train on enormous data using pre-text text and develop a highly meaningful latent space that predict picture statistic for picture statistic. For downstream tasks, they conditionally fine-tune the semantic space to map task-specific circumstances. The machine learning create the believable visual based on pre-trained information. Pre-trained model increase picture quality and variety compared to from scratch technique. Conditional image synthesis create high quality picture that match the condition. Computer vision and graphic use it to create the manipulate the information. Large scale pre-training improve picture categorization, object identification, and semantic augmentation. Lastly, conditional fine-tuning lets downstream tasks use the same pre-trained model. Pre-training allow training a generative model with less training data. Next is the Xformers. So Xformers offer a straightforward composable way to build transformer. The core of Xformer is a modular collection of transformer components, along with the configuration factories for flexible transformer models. Additionally, Xformer abstraction make it simple for us to create our own models. Every model that have been trained and tested also had a faster runtime thanks to the use of Xformers. In conclusion, Xformers allow us to utilize the GPU more efficiently in terms of runtime and VRAM usage. So, in this study, we use MSE and RMSE as the loss function, which measure the degree of inaccuracy in statistical model. The MSE is equal to 0 when a model is error-free. Its value increases when model error does as well. There is no specific target for MSE, just depending how good we want the model is. The next is RMSE, is the residual standard deviation. The distance between the data point and the regression line is measured by residual, and the spread of this residual is measured by RMSE. In other words, it provides information of how tightly the data is clustered around the line of best fit. Based on based on other papers, a good RMSE score is between 0.3 and 0.6. We targeted the score number between this score. The next chapter is the result and discussion. This is all the model that we train based on different hyperparameter settings. Is it necessary to enter a custom parameter before beginning the training process? The decision about how to train the model is based on these parameters such as epoch, learning rate, and beginning learning rate are few significant parameters. Epoch is how many training steps that model wants to do. The more the epochs there are, the longer it takes to set up to complete the training model. Next, I try to attempt to train the model as many times as possible between 800 and 10,000 epochs. After extensive testing, the discovery that the 1,000 800 epoch had lower MSE and were more stable based on the tensor board result. Next is the learning rate. There are three learning rates that have been used for our testing. First is constant, that default learning rate schedule in the CGD optimizer in Keras. Momentum and decay rate are both set to 0 by default. Second is polynomial. You should frequently note that mono is decreasing learning rate with the well-adjusted degree and change the result in higher performing model. Lastly is linear, is a learning rate that can be degraded to 0 using the scheduler. A smaller exponent causes the learning rate to decay more slowly. A bigger exponent causes the learning rate to decrease more quickly. The value of the exponent distinguishes a linear and polynomial schedule. Lastly, learning rate is the hyperparameter that controls how parameter estimate is updated or learned by an algorithm. Based on this result that we have, we already got an RMSE score to target that we wanted. Even though it's quite big, RMSE score is still not past the 0.6 score in all the models. So next, how do we choose the best model based on the MSE? We determined that the best model by the lowest MSE score that measured by TensorBoard. We compared the test 12 and have the MSE of 0.288, and test 8 have the higher one, it's 0.294. Other than the test 12 have more stable graph than test 8. How do we know that? So these two testing use the same epoch with different learning rate. Test 8 using the constant and test 12 using polynomial. Based on the epoch number 400 in the graph, test 12 graph number is already stable and similar to the final epoch number, rather than test 8 graph that are still up and down until 400 epoch. It needed until epoch 800 to find the stability of the score. That's why we're gonna test 12 as our best model that using polynomial as the learning rate, the initial learning rate of 1 multiple 10 square mean 5. So afterward, we decide to use testing 12 like I said before. To show the test, we only need to put the text and the brand of the automobile that we need to see. This is an example of a few text input that we could put in. So our model could generate a picture based on the color, position, and the location of the automobile. So after we finished the experiment, we conclude that our model had a satisfactory performance because we got the RMSE score that we wanted. And MSE score that was very low is below 0.3 and so of that. So our model is able to make a great output into the text we are trying to input. Training time is also the problem because the more data that we need to train, the more training time is needed. This research could also be beneficial for optimism of the giving new ways to generate text to image. We hope in the future we will develop more advanced text to image a stable diffusion model that could help in many fields such as medical or maybe transportation and so on. Thank you so much for listening for my presentation. Thank you.
Thank you, Mr. Fariz. Okay, Mr. Fariz, thank you for the presentation. And is there any question for the Mr. Fariz presentation?
I do have a question, sir.
Yeah, okay, Mr. Nicholas, please.
So based on what I read, many generative models have scored below 0.2. And my question is, what kind of improvement could be done to improve the score that I've already?
Sorry, Mr. Nicholas, your question is not quite. I cannot hear your voice quite higher.
Okay. Sorry. Hello.
Yep.
Okay. So based on what I read on your presentation, there are many generative models have scored below 0.2, and the question is, what kind of improvement could be done to improve the MSE score?
Yeah. First of all, it's a very good question from Mr. Nicholas Inzaghi. So the model that we are training on right now is still based on trial and error and searching for what is the best MSE score that could come up. So it's so to possibly improve it, we could add that similar feature selection kind of stuff for our hyperparameter setting. So maybe we could find the best number for epoch that could make MSK score better, or maybe which learning rate that could have the best MSC score. Also, the much more study on polynomial, constant, and linear learning rate need to be done to make sure what is the effect of this hyperparameter to our project. I think that's the answer for that question.
Okay, I get it. Thank you so much, Mr. Faris.
Yeah, thank you for the question.
Okay, thank you, Mr. Nicholas and Mr. Faris, for the presentation. I only hope that research can proceed better, as mentioned in the conclusion, that will develop a more advanced model of stable diffusion of text to image that can help in areas such as medicine and transportation. Okay, good luck, Mr. Faris.
Okay, thank you so much, sir, for the chance for the presentation.
Okay, thank you. And